F-region ionospheric variability across both polar caps. Both of these maps are equally valid physically, but we spent a lot more time looking at the Northern Hemisphere. In the past, people have drawn conclusions from Northern Hemisphere observations and then assumed that the Southern Hemisphere is the same except separated by 6 months. Today we'll address ionospheric variability across both polar caps. This is a movie of total electron content in the northern polar cap. Total electron content is the height integrated ionospheric electron density. In this case, it comes from the University of Bath's MIDAS GPS-based tomographic algorithm. Geographic north is marked, and Africa is visible in the bottom of the image. So we can see dense plasma in the sunlit day side at lower latitudes, and this is convected into the polar cap as a tongue of ionization, which then breaks up into polar cap patches. This phenomenon occurs at most times of the year, but it's rarely observed in June or July. And the reason for the summer minimum has been presented as a reduced contrast effect. So the tongue of ionization is supposed to be obscured by high ambient densities in summer. And if that's true, then we should see the same pattern except shifted by 6 months in the southern hemisphere. Satellite data have been used to count electron density or TEC spikes to get polar cap patch occurrence rates in both hemispheres. Multiple different approaches have indicated minima in the northern hemisphere summer, including the two that I've shown here. So the delta n over n test requires that the spike is larger than some multiple of the background, usually more than double the background. The delta n test requires simply that the spike is larger than some absolute value. It could be 4 tech units, or it could be 10 to the 5th electrons per centimeter cubed. In this case, it's 4 tech units. So what we see here is that both of these approaches have a minimum around the June solstice, and the delta n test also has a solar cycle variability where the ionization level has decreased between 2014 and 2017, and that causes the counts to tail off there. So based on the explanation I presented earlier, we predict the same thing but shifted by 6 months for the southern hemisphere. So that's what I've tried to draw in here. You have just a 6-month shift in the maxima of the two sets of statistics. So when we look at the data, the delta n over n test yields approximately what we predicted, but the delta n pattern is very strange because it doesn't have any shift. So the pattern follows actually the same calendar months in both hemispheres. And that strange result was first reported by Noya et al. 2013 and has since been confirmed by other authors. And today we're going to look at why that strange pattern occurs. So as a case study, for ground-based validation, we've selected 1 to 28 January and July 2014 so that we can capture the extremes of the pattern in the most recent solar maximum. As a data set, we'll use the ground-based GPS TEC that from the MIDAS algorithm that was shown earlier. And we're using TEC because it's a reliable proxy of the F-layer electron density. The model is SAMI3, and we're using the FISM solar flux data, the Weimer potential, the Hardy precipitation, the HWM winds, and the MSIS neutral composition. So this model is completely independent from the data, but it's a statistically accurate representation of the physics in this case, and I'll show evidence of that later. So the 2 months actually have very similar insolation and IMF conditions. So the F10.7 index of solar flux is around 155 in January and around 141 in July. The IMF-BZ has also a similar standard deviation, 2.1 in January and 2.5 in July. So I think these 2 months are a good comparison period. So here we're showing images of total electron content from the Midas algorithm. The GPS ground stations are shown in red. The coverage is much better in the north. The 60 and 70 degrees magnetic are shown as the black contours. Noon is indicated by the black dots at the perimeter. And what we can see at the top left image is a tongue of ionization starting to form from the American sector just post-noon, and it's just pushing its way into the polar cap there. In the bottom left, we can see a similar structure, even denser, which is cutting across the western part of the continent. And in July, the polar caps are a lot more uniform. So the north has high densities than it did in January, of course, but it doesn't have the same strong structuring. And the same is true in the south, where actually the densities are very low, but once again, it's very uniform in July. So now if we look at a statistical breakdown of all the TEC values that were observed above 70 degrees magnetic in the test period, then we'll show the standard deviation in blue, the median in green, and the range in red. So if we look at the range there, the range of TEC values is much larger in both hemispheres in January than it is in July. So that matches that delta N test and the result that was first shown by Noya et al. In 2013. So what we see also here, that range is really tracking just the long tail of values. It doesn't have much to do with the bulk population in the polar cap, but it does extend just to capture the tongues of ionization and the patches. Those are a tiny fraction of the whole number of TEC values in the polar cap, but they do make up the highest and most dense part of the populations. So the bulk population, which is much less dense, there the median and the standard deviation always follow the local summer. So they're larger in local summer than in local winter. So if you look at it that way, actually the north is the paradoxical case, because the range in January in Northern Hemisphere is much larger than the range in July in the Northern Hemisphere, whereas in the south the range follows all the other values. So yeah, if we focus in on that July north case C there, that tail cuts off very early on compared to all the others, especially compared to Northern January, extends much further than it does in Northern July. So another thing to note here, the south appears to be far more variable than the north overall, with the range going up 50% higher in the south than it does in the north. And so we'll try to use the SAMI3 model to understand what's going on here. So if we look at the January cases, both in north and south, the model does a very good job of predicting the tongues of ionization, showing the same location and approximately the same magnitude, maybe a little bit lower in the January cases. And it really fills in the gaps in the southern hemisphere, showing how that tongue of ionization can spiral in from way there over in the late evening across Antarctica and towards the magnetic pole. In July, we can see that the polar caps are both a lot more uniform, although there is that tongue of ionization coming in the north, again from the late evening in July. So now let's take a look at some movies to get an idea of the dynamics. So the Weimer potential pattern is overlaid on the SAMI3 results below. The solar and geomagnetic indices are shown on the left. We can see that tongues of ionization form almost every day from the European American sector as plasma is convected in from the day side. So that's where the high latitude convection pattern reaches lower geographic latitudes, and so it can access the densest plasma there. So now if we look at the July movie, we can see that the polar cap TEC is higher than it was in January, but we don't see the same intense tongues of ionization. When we do see the plasma convected in, it tends to enter from the late evening and still usually from the American sector. So if we do the same statistical analysis that we did in the data on the model, then we can see pretty much the same patterns are retrieved in both cases. The tails on the model are not quite as far out, but we still have the same pattern of larger ranges in January than in July. So why is there a June-July minimum in high latitude variability across both hemispheres? Well, actually there are two reasons. Number one, globally there's 30% more ionosphere in January than there is in July, in part because the Earth is 3% closer to the Sun. So the plasma that's available to be convected into the polar caps is much greater in January. Number two, the F-layer plasma lifetimes are much longer in the northern winter polar cap than they are elsewhere. So in the north, the average O+ ion lasts 56% longer before it recombines in January than it does in July. So any plasma that's convected in can survive much better in January. And so this explanation was first proposed by Wood and Priest in 2010. In summary, the range of TEC variability is larger in January than in July 2014 in both polar caps, which supports the result of Noya et al. In 2013. The southern polar cap is far more variable overall, with maximum values around 50% higher than they are in the north. The January range is greater than the July range because, number one, there's 30% more plasma available globally, and number two, the plasma lifetimes are the longest of all in the northern hemisphere winter and the shortest of all in the northern hemisphere summer.